All right, almost ready. Let's see. Get that. All right, sorry about that. Let's go ahead and start. My plan was I'm just going to finish up talking about the PCA, so good, kind of go into the details. So I don't know if we'll spend the whole time today talking about stuff, but we can go into a little bit of details of the mechanisms and the math and things on that. So. Before I jump into that, this is the reason why I'm going to do this is the second part of the assignment 6 that hopefully everybody's working on now is kind of doing PCA. So part 2 is doing a PCA by hand. So both the parts, like we mentioned last time, we're kind of building these mechanisms by hand. So building a simple k-means clustering and then building a simple PCA. So to do the PCA though, we do need to. So when you're implementing the part 3 of the second one, we do have to kind of reuse the singular value decomposition from Lin algebra and a couple of other steps here. So. So we'll jump into that. So besides that, so remember that we've got this week and next week where we're working on unsupervised learning mechanisms. So we haven't really. We'll talk in more detail about the k-means, clustering, and clustering in general then next week. So that was actually the first part of the assignment. So. We've only got 2 more full weeks after the end of this one, just to remind people where we're at in classes and stuff. So, but the 6th assignment will be due at the end of next week. So then we'll concentrate on some review and doing the second test on the final full week of classes. All right. I've been still kind of behind on some stuff, but I don't think I've gotten too many questions yet about assignment 6. So, if you are working on assignment 6 and want to have a question about something, do send me an email. Okay, so for the rest of the time, I'll just go ahead and kind of go through the last part of the class notebook that I had on PCA, which is material mostly from our textbook. So, and again, I'll also kind of mention I do recommend using Dr. Ng's lectures as well. So he had a pretty good sequence on principal component analysis. So if you want to get some more of the details, I think that even you'll get from the textbook. His videos are some good things to watch. So. Last time we had done kind of just a very simple example. We'll continue using this data set. So, it's really only has two features, and we're applying PCA to it just to show, so we can still visualize the results of what happens when you do this. And we mentioned before, so we would normally, you wouldn't want to do this by hand. You'll want to go ahead and normally use PCA from scikit-learn or a similar machine learning library. So it'll do the things for you, including also doing the normalization that is needed for PCA to work correctly. So you don't have to worry about that beforehand if we're going to use PCA from scikit-learn. Yeah, so I was going to mention a little bit about the matrices that you get back from here. So let me bring up the textbook also real quickly so I can show something. So also if you did the reading on the textbook, it does go into, some of these details here. PCA is really using this technique known as singular value decomposition. So really it's taking the original matrix and decomposing it into these three different matrices, the U, sigma, and V. Well, V is actually the principal, the vectors, and then U and sigma are two more that get decomposed into here. So anyway, it is worthwhile. So yeah, I'd kind of forgotten. There's an example of actually, doing the SVD by hand as well. Not to mention also centering the data. So just again, instead of using scikit-learn. The easiest way to center data is just to subtract the mean value. So really, this kind of thing. So we also do this in the class lecture notebook. So this is really making certain the data is centered around the origin for all these. So this actually does this for each individual feature that you have here, if you kind of know what's happening, because this calculates the mean. So you return back a mean when you do it on axis 0 of each one of your columns or each one of your features in X. So then you're subtracting that mean for, so if you have 100 features, you're actually centering every one of your features by doing something like that, right? So if when you're doing this by hand in the assignment, the SVD call does actually return back the three matrices, that U, sigma, and the V here. So I wanted to mention, I thought, I'm misremembering, so okay, so let me go back to the notebook from the classroom. So you can get the same components from those same matrices from calling PCA and scikit-learn as well. So by accessing particular member variables from the resulting fit when you do it here. So yeah, I want to talk just a little bit about this. So this is really corresponds to the the sigma matrix, and this is really the V matrix. So so when you're using PCA from scikit-learn, so if you want to understand the details of this a little bit, this one is the vector portion of decomposing this into three separate matrices here. So this should give you, this should sum up to 1, although Yeah, I can't remember exactly what it was. Normally you see that 1 or close to 1 if you sum up all the results of the B here. So these give sort of the relative amount of variance. Yeah, so kind of as the name implies here. So the amount of variance for each dimension, and these will be supported here. So the resulting transformation that was found from doing the singular value decomposition, the principal component, the one with the most variance, explained approximately 76% of this. And again, usually this sums up to 1, so I can't remember. So in our assignment, probably it'll be 1 or close to 1 when you look at these. So, for this data set, we only had 2. So the result again is just 2-dimensional. So the second dimension had that amount of variance that was kind of covered by the second one that was selected here. So this first one, I won't go into it, but for those interested, this is really the matrix that you can use to transform the original space. And that is used in this method to draw the vector. So I think there's kind of a copy of this in the assignment that you're working on. So you can kind of plug in. So as long as you do the singular value decomposition by hand, you'll get back these components, and these can be used then basically, these are what are being used to determine what the vector was of the first principal component when projected onto the original space. This drawing came out from that first matrix and then the second vector as well. So those are coming from the calculations in the little loop there, where it's going through each one of the 2 principal components that we had in the components in the explained variance here, in order to calculate and draw that these vectors representations on there. So. So where's I was looking for the equation. Is that in the assignment? So some of the stuff in the assignment kind of comes from the textbook, and some comes a little bit from Dr. Ng's lectures as well. So, for example, maybe I'm missing it, but right, the actual thing that you pass into the SVD method of the linear algebra library, you have to do a little bit of transformation. So not only do you have to center it and normalize it, but you have to perform this transformation on it as well here. So So I'm looking at the assignment right now. So when you implement this by hand, you are supposed to be passing in this, and then actually returning back the U and the S matrices here, and also we ask that you return back the centered, so the centers for the original data X. And the standard deviations for each one of the features, so we can use those when we kind of do the reverse of, when we reduce and then reproject back the data, we kind of need the original mean and standard deviation of each one of the features that we had in X that were passed in here. So So, Oh, so yeah, that whiten parameter for the scikit-learn's version of PCA will come into play a little bit here when you're doing this on the assignment. So kind of like centering using the mean normalization, you sort of have to always do. But I guess that the scaling, so that all dimensions have the same standard deviation, is not really strictly necessary for PCA. So yeah, that's kind of what that whiten parameter is doing here. So if you don't specify that, the default is not to do that scaling. So the default will be false. So that's kind of what the difference is between these two things here. If you read through the notebook from the textbook here, so when we reproject into our new space, things are going to be rotated like this, and if we do the scaling, so now, these vectors are approximately the size of the amount of variance, right? So here variance is really just the spread in each of the dimensions that we have. So our principal component has a large amount of spread, and that's kind of be captured by the length of that vector, and then our second dimension from the singular value decomposition had quite a bit less spread, right? So and because we only have two dimensions here, the second dimension was fixed. It had to be orthogonal to the first one. So if you take that and rotate it, but if you also normalize the standard deviation, so normalize it so it has approximately the same amount of spread, you get something like this. So this is not only rotated, but we've normalized, so both of them have approximately a standard deviation of 1, I think, if we do it. So that's basically kind of what's happening on the whiten parameter from scikit-learn. So, and that's what we're doing here on the second subplot. Okay. So our textbook doesn't maybe go into as much detail as Dr. Ng's lectures do, but really, so an important step when you are doing this by hand is you're not really just passing in directly the matrix. It needs to be this covariance matrix. So really, the singular value decomposition is on this thing that's known as the covariance matrix. So covariance is really kind of it's really a measure of the amount of similarity between the features and each feature with every other feature. So that's kind of what we're computing by hand here. So if you just take the matrix multiplication of the transpose of X with itself, and divide, and then take the average of those. So divide it by, divide by the number of features that you have here. So not really the average, but really sigma is actually like a square matrix, but it's this covariance matrix of the original X data that you're performing the singular value decomposition on. Or in this example notebook for the class, we're performing it after we've done the normalization. So we did the centering, and also potentially, if we want to, you can do that on the centered and the things that are scaled by the standard deviation. So, And I can't remember exactly what we asked for in the assignment, so I could be wrong here, but I think that when you do it by hand, you are supposed to be, is this right? So in your PCA, you'll have to do that same thing to calculate the covariance, but you'll also need to reuse your feature normalize. So the first thing that you're supposed to do on the assignment, you are supposed to be scaling both of those. But so you're supposed to be centering. Feature normalize is supposed to both be centering and scaling by the standard deviation. So presumably, since you're reusing this function, when you'll have it centered and scaled, each feature centered and scaled before you do the covariance and then perform the singular value decomposition by hand, essentially, in your second function for this assignment. So back to this. So you do get, so part of the assignment when you look at it is just to kind of convince you that you are doing exactly the same thing that scikit-learn does. So the mu, the sigma, and your vector that you get back should end up being the same or almost exactly the same as the one that you would get when you do it, when you use the PCA from scikit-learn, assuming that we've done the normalization correctly in the same way and all that kind of stuff. So again, if we look at this here in the notebook, this should have been the same as what we had when we did it on the first part here in terms of the components matrix and the explained variance. So now when you do it by hand, we've got the what we call the U sigma and V, or USV decomposed matrices here, but again, the V should be the same, and it doesn't look exactly the same, does it? So here in the notebook, the difference. I guess that is the same, right? So the depending on whether you whiten or not, the components here, which are coming from, which are really just directly the U matrix from this decomposition, might be a little bit different depending on if you do that normalization on the standard deviation or not. So, but those are, I guess, the point to come back to that, to summarize on that. The point is that the PCA that you do from scikit-learn is really just returning U for the components and V for the explained variance. Okay, those are directly coming out performing the singular value decomposition here. Okay, and intuitively, I don't necessarily have to know linear algebra and what you're doing, but for example, this matrix here, the U, this is really just a matrix that captures what the transformation is. So basically, both the rotation and the scaling can be done from this resulting U that's passed in here, right? And that's we're showing for people that are interested in the details. We're really using that matrix, we're using the components here when we call when we do them directly. So just looking back at the first time that we drew the result from that. So basically, this draw vectors in here, we're passing in the It's a little bit tough to follow the code maybe, but we are actually pulling out. This calculation here is doing a little bit of linear algebra to pull out the individual vectors that are these components, but it really is pulling that out of the components matrix here from scikit-learn, which is the U matrix, as well as the V as well. So this one, the length. So by multiplying the length, that's how we scale it. That's how we get an indication of the amount of variance explained by each of the principal components. But this first one here is really the vector, which is an indication of the direction that we ended up rotating or finding for that each component that we're doing in this loop here one by one when we draw or when we calculate those on these figures. So like we did it this first time, we could do this, or if you do it by hand, you can should be able to directly use the U and the V the same way, because those should be the same thing that are used here from scikit-learn. So components is really the U matrix from the decomposition, and the explained variance is really the V from the decomposition that we do. So when you actually do the fit for scikit-learn, then so you can ask it to give you back, the transformed data set X, right? So to do that by hand, it's really just a matrix multiplication. So again, it's really just that U matrix. So you can do it all in one matrix multiplication. If you take the original X matrix, multiply it by the U, you'll get the transformed data set, right? So again, these features, hopefully people are clear about that, right? So these features that we call component 1 and component 2 back here are not the same as the original feature 1 and feature 2 that we had, right? So these are rotated and scaled. So component 1 does not correspond to X. It corresponds to the distance along that vector here, and component 2 corresponds not to the second feature that we had in the original X, but to the distance from this component after we scale there. So again, where was I? So yeah, I mean it's relatively simple. I think this is like the third and the fourth step here for the assignment that you're supposed to be doing. So to transform it. To transform it and project it, basically. So transforming the new into the new state is really just a simple matrix multiplication, which we're kind of doing there. And if you want to so in the notebook I had for the class, I only showed doing the dimensionality reduction using scikit-learn. So, for example, this is one of the main things that PCA is used for, is to actually reduce some really high dimensional data set into some number, a lower dimension, so some number of the more important features. You can do that directly using the PCA from scikit-learn right at the start by specifying the number of components that you want to keep. Okay, we're doing that same we're using the same data set still here, but by specifying the number of components to compete, and then when we do the transform, it's doing the dimensionality reduction for us, so we end up with just a single dimension. Right? And here we're showing, this is kind of the last step that you're supposed to be doing, but you have to do it by hand. So anyway, before I skip over on this, so if you're doing this by hand, really all you have to do is when we get our transformed data set by doing the multiplication, if I want to reduce dimensionality, I just use the number of columns, the number of features that I want. So it's really just a slice on the matrix to reduce the dimensions, right? So again, if this one we've only got 2 dimensions, so we only end up with 2 columns after doing the dot product. And if we want to reduce it to one dimension, we would use column 0, the most significant dimension that we had from the singular value decomposition. If we have a much higher dimensional space, we could use whatever number that we want. And again, that's another useful another use of the V matrix. So that if you think of those as the amount of explained variance, and if that sums up to 1, you can determine what number of dimensions that you want to keep by, like if I want to keep 80% of the explained variance, I could just keep the dimensions that sum up to 80%. If I have a lot more than 2 here. So that's a typical thing that's done with the V. Right? And that's another way that you can specify when you're using scikit-learn. So instead of specifying an absolute number of dimensions to keep, you can specify a floating point number between 0 and 1, so the amount of variance to keep for n components, I believe. And it will, let me check that, but probably have to rerun my notebook here. There we go. So right, if the number of components is a float, it will select the number of components based on the amount of variance that needs to be explained based on a percentage. There's a final thing, let me see here. So let me just mention about the kind of the last step here. So hopefully, the descriptions of this will help you for these steps as well. So in terms of dimensionality reduction, so yeah, the project data is need to be passing in sort of the U matrix. So you have, in order to project the data, and then if that's not clear, it's basically yeah. So we're giving some kind of some examples here that Oh yeah, another way to do that is just before you do the multiplication times u, you can just slice out the column that you want and then do the multiplication. Then you'll end up with the projection on the number of dimensions that we asked for. So k in this case, the top k component. So, I think you can do it either way. So you can actually just do the multiplication first and do the slice afterwards, or you can just slice u and do the multiplication with that one. Should get the same result, I believe. So on the end, on the recovered data, the last task here, the idea is that we want to reproject it back into the original space. So the idea on this one is so I'm trying to remember. The basic idea is, your recovered matrix will be back into the original space, but so if you're recovering from a low dimensional space, though, you will end up having removed the item, the dimension. So in this case, since we're recovering from our original two-dimensional space that we had reduced down to one dimension, recovering back to two dimension, you'll end up with everything projected back onto the line here. So if we had examples of things like that, like here, right? So. But basically we have to do kind of the same thing by hand. So instead of using scikit-learn inverse transform, we'll be doing the those same step as a matrix multiplication in order to project this, reverse this back and project it back into our original, in this case, feature 1 and feature 2 here. Okay, well, so I don't know if that's helping too much. Maybe as a final thing, we still got a little bit of time. So there were a couple of examples, if you did the readings on the textbook. So, I thought I would mention this here. So, one thing that I did talk about, the explained variance, I guess maybe it's the explained variance ratio that you have to use from scikit-learn. So that should sum up to 1. So maybe that's why it wasn't quite getting what I was expecting here. I've just forgotten. So yeah, originally when we'd done this with scikit-learn, so yeah, I guess there's two separate things, explained variance and explained variance ratio. So it's really that. So there must be a translation, some sort of a transformation that's done on the raw vector v to get the ratio. So it probably it's just redone in order to normalize it so that it sums up to 1. I'm guessing. But yeah, using scikit-learn, so that's a useful kind of thing. So for example, when we did this on the, I won't go into details, we're using the MNIST data set here. And performing a principal component analysis on it. So in that one, we had the MNIST data set had a 64 components, so it was 64 dimensional. So what was it? That's the number of rows and columns in the images that we had. So yeah, this data set we're using must be just 8 rows and 8 columns for our pixels that we've fit the MNIST digits into. Just looking at the results, so looking at the explained variance here, so using the cumulative sum, we can get some idea of reducing it down. So for example, if we wanted to reduce this down to some number of dimensions where we're still keeping 90% of the information, so 90% of the explained variance, that would come somewhere approximately around there, right? So somewhere approximately around, we would only need to keep the first 20 principal components of the 64. Right? And that's not atypical when you're doing this kinds of dimensionality reduction with PCA. So often, this explained variance rises relatively quickly. So you need much less than 50% or 25% of the total original features to explain a fairly, to capture a large amount of the information that's in the data set. Okay? So that's kind of what's being discussed on the last part here, where they use PCA for on the MNIST data set from our textbook. So, and another thing, I don't know if I mentioned this before, but often a lot of the information that's in a data set like this that's at the end after you approach a component analysis, there's a lot of noise in that. So often you're losing very little information. If you pick 80-90% of the explained variance to reduce your dimensionality down to. So often you can get pretty much about the same performance, but with a greatly fewer number of dimensions if you are able to do this kind of transformation before you do a training on a data set, right? So again, 64 isn't really that large of a data set, but if you're working with data sets with thousands, tens of thousands of features, it begins to make sense in terms of computation and performance and things. Here's another one. So you're using this. So this was another data set where there was 144 or so features here. Same kind of thing, although so it's not always true. So here, if you want to get to 80 or 90, you do have to use over half of them. So. Okay, that was kind of all that I kind of wanted to touch on today, so I'm going to stop a little bit early because I don't have any other useful stuff to say on some of these other things. So I'll stop there for today. So let me know if people have questions. Working on PCA, so especially like maybe the very last thing you're supposed to do on PCA by hand, you might have to kind of watch through some of Dr. Ng's videos. I don't know if there's a real good explanation for that on the textbook or thing, where it talks about the actual details of how you do some of that by hand to reduce and then to reproject, for example. So, next week then we'll go back to the first part of the site and we'll talk about some clustering and stuff. So I'll probably have some more stuff to say about clustering. So not only the thing that we're going to look at, but a couple of other techniques that are covered in the textbook. So, all right, yeah. So that's it. I'm just gonna stop there. So,